In this video, we're going to take a look at how we can use differential equations to solve another type of problem with non-constant acceleration. So in this problem, we're going to have an incline, and there's going to be an object on the incline of mass m, angle here is theta, and there's going to be a resistive force, maybe due to air friction or something like that, and its magnitude is BV, where B is a constant and V is the velocity. We're going to release this from rest at time equals 0, so the velocity at time equals 0 is equal to 0. And I'm not going to put units here because this could be any arbitrary units, but when time equals 0, at 0 velocity, so it's at rest, so there's no force here. But as this accelerates downwards due to gravity, mg sine theta to be exact, this resistive force gets larger and larger and larger, so it's not constant. So we can't use the kinematic model to analyze this. In this problem, what we're going to do is we're going to find, what we're trying to find is an expression for the velocity as a function of time. And just to recall, this is not a constant acceleration model, so it's not equal to our usual v0 plus at. It's going to be something different than that because the acceleration is not constant. So that's out. So we want to find this equation. So this is a force model type problem. So the first step of this type of problem is to draw the FBD. So if we draw our FBD here, step 1, FBD, we have our object here, and I'm going to draw mg straight down. I won't break it up in mg sine and cosine yet, I'll just say mg down. The normal force from the platform, the incline, and then the resistive force, again, maybe due to air resistance or something like that, up the incline. Step 2, we're going to sum the forces. So we're going to sum the forces in the x direction. I'll have down as the positive direction since it's going to slide down the incline. Equals m ai equals, and we're going to sum the forces in the the y direction. M A J. So without going into the sine and cosine thing, I think we know now that this is in the x direction, and mg sine theta minus bv, and it will accelerate. And the y direction, we have the normal force minus mg cosine theta, and this is 0 acceleration. There's no acceleration in this direction. So again, our goal is to find the velocity as a function of time, and this is the non-constant acceleration, so this is going to be equal to, I'm going to write a differential equation, ma, or m dv dt, because this is basically acceleration. Okay, so let's solve. Let's go through this solution, and in this one you can see that we're going to have something slightly different than the previous example. We're actually going to have to use a u substitution. So I'm going to map this out step by step so we can follow along here. So I'm going to take the first force equation, and basically what I get is mg sine theta minus bv equals m dv dt. And again, we're trying to solve for v as a function of time. So we want to, just like in algebra, isolate the variables, get all the v's on one side and all the t's on the other side so we can solve for the velocity. Step 2, and I'm going to go through this in lots and lots of detail so you can follow along here. I'm going to do the separation of variables thing. I'm going to bring the dt up. I'm going to bring this entire term here down. I'm going to cross multiply. So I'm going to get a dt, and I'm going to bring that m down as well. So that's an m there. Equals a dv over a lot of stuff. mg sine theta minus bv. So we have all the v's on one side, all the t's on the other side, so it looks good. And the way we solve for v is, because we have a differential here on both sides, we're going to integrate both sides. So step 3. I'm going to integrate dt over m, and over here I'm going to take a integral, and this is dv over mg sine theta minus bv. So we can't directly use the logarithmic rule because we have a constant sitting in here. This is a constant. M is constant, G is constant, and theta is constant. So we have a constant in here that kind of doesn't allow us to use the log rule, but we're going to use a u substitution. So the form of the u sub is a constant minus a constant times the variable. I'm sure you've seen that in calculus class. So we're going to take a little break here and do a little side dish. We're going to let u equal the denominator, mg sine theta, which is all constant basically, minus bv. Therefore du, be careful my u's and v's here, is equal to the derivative of a constant is 0, and the derivative of this term is minus b dv. Therefore dv is equal to du. The u is going to be a little rounded compared to my v's, over minus b. So I can rewrite the integral. So after this little side dish here, I'm going to go to step 4. And I'm going to rewrite the integral. So this is a dt. On this side, this doesn't change. Over a mass equals. And this is what? Well, let's see. What's a dv? A dv is a du over a minus b, right there. And this denominator here is just u. So we have something that looks like a logarithmic type thing here. I'm going to bring the b and the m's are constants, so I'm going to actually bring the b's over here. I'm going to bring that minus b on up top here. And I'm going to get a minus b over m. And the antiderivative or integral of dt is simply a t plus a constant. I'll call it constant 1. And on this side, we're going to get a du over u, so this is ln of u plus constant 2. I'm going to play that same game. I'm going to bring the C2 over here with the C1, call it a new constant C3. So this is 5, 6, step 6. So this is minus b, and I'm going through every step here, so you could probably do a couple of steps here a little more easily. ln of u. Now we want to solve for the velocity. So remember that this u is really this business. Okay. Let me clean it up a little bit. I'm going to take e to the both sides, e to this and e to all of this business here. So it's going to give me on this side a u equals e to the minus b over t m over m times e to the c3. And a constant times to a constant is really, again, this is another constant in disguise. So I'm going to call it c4. So in the next step, I'm going to replace this with the c4, and then I'm going to take the u and substitute it back in. So let's see, that would be 8, I believe. So the u is an mg sine theta minus BV equals C4, I'm going to put that C4 right here, equals C4 e to the minus B over T times T over M. And I'm going to solve for V. So I'm going to do a little algebra here and solve for V. So if you follow along here with me, this in step 9 here. V is equal to, and what I'm going to be doing here is bringing this over here and this business over there and dividing by B as boy. So V is equal to, if I do this right, mg sine theta minus C4 e to the minus bt over m, and then I'm going to divide by the b. Okay, so this looks pretty good actually, except for this little constant. And remember, when we have a constant, there's an initial condition that's given usually, and that's the initial condition. So it says at time equals 0, the velocity is 0. When time is 0, the velocity is 0. So if I go to step 10 here, when t is 0, this is 0. So 0 equals mg sine theta minus C4 times e to the, this is all just basically 0. Because when t is 0, it's e to the 0. All over b. And so I want to solve for this constant. What is the constant? Like what actually goes right there? Once I solve for it, I can plug it back in. So if I look at this a little more closely here, if I multiply the b times the 0, that's still 0, so that b basically disappears. And I'm left with, lots of steps here, 0 equals mg sine theta minus C4, and this is basically 1, right? So that's just 1. So C4 is, lo and behold, mg sine theta. So what's that do for me? Well, what it does for me is I take this step here, my velocity is a function of time, now I know what C4 is, and so my final answer, finally getting there, is my velocity as a function of time is equal to mg sine theta minus C4. What's C4? mg sine theta, I'm going to run a space here, times I'm going to put a times here. Sorry, I ran out of room. There's a multiplication sign there. Times, continue it down here, e to the minus bt over m. Hope you can read that. And then I'll just factor out, I'll do one more step just to factor out, maybe I can fit it in here. So step 14. The velocity is a function of time is equal to mg sine theta 1 minus e to the minus bt over m. That b comes out over here as well. And there's my velocity equation. So it's a lot of steps, and I broke it down in lots of detail. But basically, from the force equation, I have a situation where I have something that looks like a log, but there's a constant sitting in front, which leads me to the u sub. Here's the u sub. I perform my u substitution, perform the integration, which gives me a log. And the thing that arises is this constant, which I have to go back through and use the initial condition to find, which I did right here, to find what the constant is. And the constant was found here is mg sine theta. I plug that back into my velocity equation to get something in terms of known variables. I get a little factoring here to get a final equation. So once I get the velocity equation, Here I could take a derivative to get the acceleration equation. I could take an antiderivative to get the position versus time. But nonetheless, the velocity equation looks very different than the simple kinematics model here that we have. But as long as we have a differentiable function, which we do, you can find that velocity equation and just keeping track of all the algebra here step by step. Now, lots of steps here. So there's an example of how we use differential equations, and specifically U sub to solve a problem involving non-constant acceleration.